Okay, so today I'm going to discuss some limits involving L'Hopital's rule, some of these slightly trickier ones that aren't obviously using L'Hopital's rule in some obvious way. But you can still apply L'Hopital's rule to get an answer out of them. So I'm going to start with this limit here in front of us, which is the limit as x goes to 0 from the right as of x to the power of x. Now, this is going to be kind of tricky because it's obviously not in a situation where we can obviously use L'Hopital's rule. It's not a fraction. Typically, when we think of L'Hopital's rule, we think of a fraction in one of these indeterminate forms, 0 over 0 or infinity over infinity. But what we can do is we can turn this into something where we can use L'Hopital's rule. So what we're going to do is anytime we see an exponent and we're trying to take a limit and we don't really know how to deal with the exponent, one of the tricks that we have up our sleeve is using logarithms, because logarithms work nicely with exponents. But we can't just throw a logarithm at this because we need to make sure that we're not changing the problem fundamentally. So we actually have to use inverse functions. So we take the limit as x goes to 0 from the right, and then we take the exponential function, so e to the power of the logarithm of x to the x. Okay, so again, just as a reminder, the exponential function of something is, if I put some blah 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 in here, this is the same as just saying e to the blah blah blah, right? So it's just a different notation when you start raising e to some more complicated powers. It would look messy if I did that. And now this is, you might be wondering why we had this 0 to the plus, and like when are we going to have to use that? And really this 0 to the plus is just because, as you can see here, we're going to take the logarithm. We took the logarithm of this, and we can only take the logarithm of positive numbers. And so because of that, we can only be plugging in numbers that are positive. And so x to the x, if this was something, if we were approaching this from the left, we might have a negative number here, and so that would be a problem with the logarithm. Also, there's some other problems with using negatives here. If you look carefully at it, maybe you can think about it. But generally, we want to the positive just takes care of the fact that the domain of the natural log is the positive real numbers. But from here, then we can kind of be tricky, do some trickery here, and we can say that this is the limit as x goes to 0 from the right. Oh, oops. Actually, no, we don't want to jump straight to the limit. The point is that we want to use the fact that the exponential function is a continuous function to then move this limit on the inside. So we can say that this is the exponential function of, and now I'm going to swap my colors here for just a second, and I'm going to say that this is the limit as x goes to 0 from the right of the natural log of x to the power of x. And all of this is inside of our exponential function. So all I've done going from here to here is moved this limit inside of the exponential function, again using the fact that the exponential function is continuous. And once we have it this way, now we have this limit on the inside, which I've highlighted in green. And what we can do is we can just work on this limit, and then whatever answer we get for this green limit, we just plug that into the exponential function, raise e to that power, and that is our final answer for the original problem here. So we're just going to go off to the side here and say, what is the limit as x goes to 0 from the right of the natural log of x to the power of x? We're just going to do this limit here, just the limit on the inside of the exponential function. Okay, and then we're going to use that answer to get the final answer here. Okay. And to do this, we're going to use the rule of logs. Okay, so the rule of logs tells us that if we have an exponent on the inside of the natural log, then we can move it to the outside as a coefficient. So this motion I'm doing with my cursor, I'm taking this exponent and moving it out front as a coefficient. So this becomes the limit as x goes to 0 from the right of x times the natural log of x. Okay. And if you've seen some of these, if you've been following along with some of these L'Hopital rules type problems, then this should look familiar. And from here, we can actually use another common trick. When you have a product and you want to use L'Hopital's rule, it can sometimes be helpful to turn the product into division by the reciprocal. So in other words, we can turn this this function x times the natural log to the natural log divided by 1 over x. Okay, so instead of multiplying by x, we're dividing by the reciprocal of x. And that's algebraically equivalent, but in this case, it's more clear to see that this is in an indeterminate form because we get negative infinity over infinity for our limit here. So we can compute that limit using L'Hopital's rule because we have a negative infinity over infinity. Okay, so we have this indeterminate form, so we can use L'Hopital's rule. So using L'Hopital's rule, remember, using L'Hopital's rule, the limit stays the same, but what we do is we take the derivative of the numerator and the derivative of the denominator. The derivative of the numerator is just 1 over x. It's the derivative of the natural log. And the derivative of the denominator, right, it's 1 over x, so you can maybe use quotient rule, but the other way to think about it is this is just x to the negative 1. And so you could just use a power rule simply and get that this is negative 1 over x squared. And you might think, oh, well, this is still somehow in a infinity over negative infinity sort of thing, so maybe we should try L'Hopital's rule again. And you could do that, but you would never get anywhere, just keep going. But what you could notice here is you can do some algebraic manipulations, and you can say that this is the limit as x goes to 0 from the right of, there's a negative sign still hanging out, and I get x squared over x. And so this is the limit as x goes to 0 from the right of negative x. Okay, and now once I have it in this form, the limit as x goes to 0 of negative x, well, that's just 0. I can just plug in that 0. And so our answer is 0. But remember, this is our answer to this limit here, the limit of the natural log of x to the x. But the limit we were originally looking for was just x to the x. So we have to take the exponential of this answer. So our final answer is the exponential of this answer that we got in green, which was 0. Okay? And more simply, the exponential at 0, we could just say that's e to the 0, which is 1. And that there is our final answer, okay, for this limit. Okay, so the big trick we did here is we introduced an exponential and a logarithm, which cancel each other out. But we did that so that we could use our logarithm rules to rearrange the original equation or function and write it in a way that was a fraction in indeterminate form, so we could apply L'Hopital's rule. And that's the general trick that we're going to try to follow for some of these other problems. That's just one more trick to try and see if it works for L'Hopital's rule. And so I'm going to try it now on this equation here. So I can once again introduce this intermediate step where I add this exponential thing. So I take the limit as x goes to 0 of the exponential of the natural log of, in fact, I'll do this in no, I won't. The natural log of 1 plus x times 1 over x, or to the power of 1 over x. And then I will move the limit inside, so I get the exponential of, in green here, it's the exponential of the limit as x goes to 0 of 1 plus x, or the natural log of 1 plus x to the 1 over x. Okay? And once again, we can, off to the side here, just compute this limit, this green limit here. So we have the limit as x goes to 0 of the natural log of 1 plus x to the 1 over x. Okay? And again, we can use our log rules, and this gives us the limit as x goes to 0 of the natural log of 1 plus x divided by x. Okay, we multiplied by 1 over x, so it's the same as dividing by x here, okay, by using our log rules here, okay. And now here, this, if we plugged in 0, we'd get the natural log of 1, which is 0 over 0. So we'd get 0 over 0, which is, again, an indeterminate form. So we can use L'Hopital's rule here, okay. So if we do L'Hopital's rule here, we do, the limit stays the same, and we take the derivative of the numerator, which is 1 over 1 plus x, and then times the derivative of the inside, which is just the derivative of 1 plus x, which is just 1, so nothing changes there. And then we divide by the derivative of the denominator, which is 1. And so we get simplified the limit as x goes to 0 of 1 over 1 plus x, which quite simply we can just plug in this x equals 0 now, and we get 1 over 1 plus 0, which just simplifies to 1. But again, this is not our final answer. Our final answer is taking that and plugging it into the exponential function. So we get the exponential of 1, which, again, more simply, is just e to the 1, which is just e. Okay? So this leads to some interesting examples where we have these sort of limits that don't seem to have anything to do with exponentials or Euler's constant or anything, and suddenly it becomes a question of the answer is e, or e something having to do with e, and so it kind of sneaks up out of nowhere. So this is one of these cases where e is very important. Okay, so that's it for this example, and I hope that you found that helpful.